We're going to continue our discussion of ISAs in this lesson by looking at data paths. Data paths are the way things are organized inside processors to allow storage of data, namely in registers, and their movements to function units for processing. Different data widths allow different types of operands to be supported, such as floats, integers, and so on. Data paths are kind of like roads for moving the data around. We need to think about what kind of data we have, where it is coming from, and where it is going. The device in charge of all this data movement is the controller. So in this lesson, we are going to learn about data path considerations, about data widths, the buses that carry them, and the function unit operations on them. Important components that dictate data paths are data specifications, data manipulations, and control flow. A question you should ask yourself as you watch the lesson: what are the special needs of data paths to be supported in embedded computing? So what else needs to happen inside a processor apart from the data path for storing the data in registers, to process it in ALU, and to read and write out of memory? Well, somebody has to coordinate these actions, and that part of the processor, which is really important, is called as the controller. What does it do? It makes sure the data is latched properly into the buffers and latches and is read properly. It also makes sure there are no hazards. It also coordinates the operations of the I/O devices and also the memory. So as far as the data path in embedded systems is concerned, especially in the VLIW computing, what it does is to coordinate these actions of data execution across those parallel instructions which execute inside a large instruction. One of the important parts of the data path has to deal with the residency of the operands in terms of where they sit, and also the results. Are they in the registers? Are they in the memory? How do they come? How do they go out of the ALU? All these things are really important, and so we'll talk about them first. Let's start with the CISC and DSP processors. So one of the important characteristics of CISC and DSP processors is that all the operands reside in memory. So there are lots and lots of instructions which have to do with memory-to-memory operations. And in addition to those, there are complex addressing modes which allow you to fetch the data in a variety of ways from the memory and also store it. In addition, especially in DSPs, there are specialty registers to hold the partial results so that we don't have to go to memory very often. For example, in multiply accumulate instructions, we keep adding the results of multiplications in a specific register called as accumulator. Remember that signal processing is all about a lot of different kinds of transforms, and one of the key operations there is a multiply accumulate. So what are the implications of these specialty registers and specialty addressing modes? There is an opportunity here, and the compiler utilizes these to perform certain optimizations to reduce the memory traffic. Now let us see how this works, the data paths for RISC and VLIW processors. So as you know, both in RISC and in VLIW, we have all the operands residing in registers before we can do any operations on them. And that means lots and lots of registers. Especially in VLIW, since we have multiple instructions that can execute in parallel, all those operands need to be in registers. So we need lots and lots of registers for them, and we have large register files to support this operation. So what is the implication of this on the compilers and its optimizations? The compiler has to perform very aggressive register allocation to make sure that all the operands stay as long as they can in those registers, and there are lots of them. And then the second activity is to schedule these instructions. The scheduling and register allocation are decoupled so that we first decide on what is best way to use the parallelism through scheduling, and then we perform the register allocation to support that schedule. One of the important parts of the data path has to deal with the residency of the operands in terms of where they sit, and also the results. Are they in the registers? Are they in the memory? How do they come? How do they go out of the ALU? All these things are really important, and so we'll talk about them first. Let's start with the CISC and DSP processors. So one of the important characteristics of CISC and DSP processors is that all the operands reside in memory. So there are lots and lots of instructions which have to do with memory-to-memory operations. And in addition to those, there are complex addressing modes which allow you to fetch the data in a variety of ways from the memory and also store it. In addition, especially in DSPs, there are specialty registers to hold the partial results so that we don't have to go to memory very often. For example, in multiply accumulate instructions, we keep adding the results of multiplications in a specific register called as accumulator. Remember that signal processing is all about a lot of different kinds of transforms, and one of the key operations there is a multiply accumulate. So what are the implications of these specialty registers and specialty addressing modes? There is an opportunity here, and the compiler utilizes these to perform certain optimizations to reduce the memory traffic. Now let us see how this works, the data paths for RISC and VLIW processors. So as you know, both in RISC and in VLIW, we have all the operands residing in registers before we can do any operations on them. And that means lots and lots of registers. Especially in VLIW, since we have multiple instructions that can execute in parallel, all those operands need to be in registers. So we need lots and lots of registers for them, and we have large register files to support this operation. So what is the implication of this on the compilers and its optimizations? The compiler has to perform very aggressive register allocation to make sure that all the operands stay as long as they can in those registers, and there are lots of them. And then the second activity is to schedule these instructions. The scheduling and register allocation are decoupled so that we first decide on what is best way to use the parallelism through scheduling, and then we perform the register allocation to support that schedule. Apart from organization of the register file and addressing modes, which we are going to visit soon, the other important part is the width of the data path. That is, how many bits are supported in the data path. So some processors would allow you to do the operation at 16-bit level. They would also allow you to do this operations at 32-bit level. The choice of these widths is really important because the number of cycles it takes to perform those operations vary dramatically. Let's do a quick quiz to test our knowledge for a very popular family of embedded processors called ARM processors. ARM processors are there in almost every cell phone and smartphone that we have. More than 90% of smartphones contain the ARM processors. There are different generations of the ARM processor: ARM 7, ARM 9, and ARM 5 STV. As far as the 16-bit multiplication is concerned with the 32-bit result, the ARM 7 takes 12 cycles, whereas ARM 9 and ARM STV takes 1 cycle. Let us guess how many cycles it may take to do the 32 by 32 operation on the other hand with a 64-bit result. Please write your guesses on this table for ARM 7 as well as ARM 9E as well as ARM STV. As far as ARM 7 is concerned, the 32-bit operations as far as multiplication is concerned takes 44 cycles. ARM 9E takes 3 cycles for 32-bit multiplications, whereas ARM 5 ST takes 2 to 4 cycles. As you can clearly see from these results, the operations for 32-bit typically take more than twice the number of cycles for the 16-bit operations. The reason why it takes twice the number of cycles than 16-bit is that the 32-bit operations are to be broken down typically into 16-bit operations, and you use the carry to perform the next set of operations, and that's why it takes sometimes even more than twice the number of cycles. So what is the underlying conclusion here? ARM 7, ARM 9, and ARM YOST support inherently a 16-bit wide bus, and in order to be able to carry out the 32-bit operations, you got to iterate at least twice, if not more, to use the 16-bit. You may ask a question, why 16-bit? Most of the operands, if they are supposed to be 16 bits, then why support a 32-bit bus? That's the design decision that is taken in ARM. And energy efficiency wise, the 16-bit buses operate much more efficiently than the 32-bit ones. So the question is, how is the width of the data path selected? Remember, the data paths couple the memory to the registers, and so the width of the data path must equal the width of the registers. Now we have two types of operands typically, the integer ones and the floating point ones. And so therefore, to support integers as well as floating point, sometimes we support two different widths of the data buses, or take a design decision that we support the data width of integers and somehow use that for implementing floating points. So that means that the time it takes to do the floating point operations is at least double that of integers. Historically, it is important to see what really happened in the embedded processors industry. Very initial versions of ARM processor did not even support the floating point operations inside the processors. So how was it done? It was done through a software library, and so it took almost hundreds of cycles to support the floating point operations. Why was it done this way? Because the other parts of the processor that deal with floating point processing were also removed, and the processor was extremely energy efficient. Let's take a look at a typical data path width in a RISC processor. Typically, memory is 32-bit. The instruction is also 32-bit, which is decoded, and the operands, which are fetched from the memory and loaded into the registers, are also 32-bit. So this is a very typical processor that is supported historically in the RISC arena. Only lately do we have 64-bit processors. However, in embedded systems, it is very atypical to support 64-bit operations. That is because most of the data is either 16 or maximum 32-bit, and we will waste a lot of energy for processing 64 bits. In addition, many CISC and RISC processors typically process the data in two different ways. We have a narrow integer data path and a wide floating point data path. DSPs, on the other hand, is a totally different story. Remember, the signal has to be encoded through AD conversion and so on, and typically those signals occupy 40 bits or 56 bits. These are odd numbers, but that is how most of the AD converters work, by converting analog signal to their digital counterparts. So since the signal is represented using 40 or 56 bits, the data path widths in DSPs is typically 40 or 56 bits. Having seen the data path widths in RISC as well as DSPs, now let's turn our attention to VLIWs. Remember how an embedded SoC or a system on a chip operates? By the way, what is a SoC? So each processor in embedded system is supposed to do a particular dedicated function. The DSP function or signal processing is typically carried out by DSPs. On the other hand, the main computing is done by a main processor, and a lot of parallelism is exploited through a VLIW coprocessor. So a VLIW coprocessor, a DSP, and a main processor typically form what is called a system on a chip. They are tightly integrated, sharing their memory and buses and so on. A typical VLIW machine has a 32-bit data path, and it could have up to 8 such processing units. Here is how a typical VLIW processor with up to 8 units could look like. So each of these are 32-bit buses to carry the data. We have an instruction issue logic which fetches this large instruction, and there could be 8 bundled together. After they are decoded, they go to the register file, get their operands, which each of those could be 32-bit operands. And since we could have 8 such operations going on in parallel, for 8 independent operations to be carried out, we would need 8 times 2, 16 data paths for supporting their operands. So the data paths shown on the previous slide had 32 bits in each part of it. They could be used for supporting integer operations. The same data paths can be reconfigured to support floating point. How? We could group them into 4 times 64, that is, each data path could be 64 bits to support a floating point operation, but we could then support only 4 of these floating point data paths. We had talked a lot about ISA, encodings, and so on, and we saw that the main operations that are there for each of the processors involve ALU operations, and then the control operations, and the third is the memory operations, and these form the minimum instruction set any ISA should support. So the quiz asks you to fill in what are the minimum instructions that are needed for supporting the memory operations. Please go ahead and write the answers now. One of the key operations that is needed to support the memory operations is an ability to load a value from memory into a register. And the second one allows us to store a value from a register into a memory unit. So load and store operations are a must, and those are important for deciding the data paths. In other words, one of the most important data paths is from memory to a register. Minimum ISA quiz number 2. Let us complete our discussion about the minimum requirements on ISA. So the question is, what is the minimum instruction that is needed to support the ALU operation? Remember again, there were 3 operations. We talked about the memory in the last slide. How about the ALU? What is the minimum instruction set that is needed for that? Please go ahead and write your answer now. The answer is subtract. Many of you might have written an answer addition, but that's not the right answer. The right answer is subtraction. Why? Because you can use subtraction to implement addition, but you cannot use addition to implement subtraction. We talked about the memory operations, we talked about the ALU operations, but that's not enough. We must talk about the control operations of the processor to be able to decide what should be the data paths. So the question is, what is the minimum number of instructions or what kind of instructions are needed to support the control functions of the processor? Please go ahead and write your answers now. So a lot of control operations are dependent on the outcome of branches and comparisons and so on. The ability to be able to decide whether the result is equal to 0 or not, that's one of the key to decide the outcome of a comparison operation. But is that enough? That is really not enough. What about deciding whether one operand is less than the other? We must have an ability to decide if a operand is less than the other, and so if the result is less than 0 is also important. The third one is the result is greater than 0. And the last one is ability to support an unconditional branch, which means to be able to go from one program counter to the other without even worrying about the comparison. The question was, what is the minimum instruction set that is needed to support the control functions? Obviously, if we can support less than, greater than comes free. So both need not be supported. So if we support 2, we need not support number 3. So what is the total number of instructions that we need to be able to support a minimum instruction set? You can see that we need 2 for memory, load and store, 1 for ALU, which is subtract, and we have 3 for control. So we need 6 as the minimum instruction set. However, most of the processors have a larger number of instructions. Why is that the case? Why do we have more than 6 instructions when minimum 6 are sufficient? We want to give many choices to the software to implement a variety of different operations, and therefore we give a rich instruction repertoire. However, choosing the operation repertoire to be supported through ISA is a very hard issue. It is really a design decision, and that considers typically the trade-offs between efficiency, how efficiently you can support it in terms of energy, latency, and so on, performance in terms of how well the application will execute, complexity, that is, how difficult it will be to implement into the hardware, and then the design and silicon costs, which are into the design cycle of the processor. Apart from these, the most important part which it relies on considers application analysis in terms of its execution frequency, in terms of its implementation complexity, and so on. Why is that important? Because finally the applications translates into the operation through the compiler, and they use those operations. And so the application efficiency is the most premium concern here. This is especially true of the embedded world, where the characteristic of the application are supremely important. Certain applications demand certain things, and therefore they must be supported. A great example is DSPs, which again need the multiply accumulate operations, and therefore, regardless of anything, that data path of multiply accumulate must be supported. In terms of different operations, those pertinent to integers in terms of integer additions and arithmetic and comparisons are most important, and therefore they form the basic units of execution. In other words, the data paths to support integers is the most important issue. What are the different implications of supporting integer arithmetic? One of the important things we need to support is carry, the other one is overflow and underflow, and some other flags. Most of the flags are implicitly set by the instructions. For example, in x86, all the flags of arithmetic operations are implicitly set. For example, carry, overflow, 0, negative, these are all set based on the value of the result. However, in VLIW, there is an additional complexity. The same flags may be updated by multiple instructions which are executing together. So handling these flags in terms of updates by multiple instructions is a very, very important issue. For example, in the VEX instruction set, we explicitly read and set the flags in registers. When different instructions execute, the flags are to be set into those registers. To understand this somewhat in details, let us see how an integer multiplication happens in VEX. To carry out multiplications of large values, we'll need large data paths, and large data paths means the multipliers are going to become very slow. Due to this reason, in VEX, we try to break down the larger multiplications into smaller units and then reconcile those partial results. To really understand this in detail, let us take a look at these 32-bit multiplications. what we have here is two 32-bit operands A and B, and the result is to be stored in C. The way we do it is illustrated by this simple C-like program over here. We try to take A and B and separate them into 16-bit entities and multiply those entities individually, and then we reconcile those by putting those together, and that becomes the result which is stored in C. In terms of VEX instructions, this is how it looks. So we have the lower parts of A and B in R1 and R2, and we have an instruction MPYLU which will multiply those 16 bits from each of the A's and B's and puts that result in R4. And then again we have other 16 bits taken from those registers R1 and R2, and MPYHS takes the higher order 16 bits from them, multiplies them, and stores the result in R5. You can see that in R1 and R2 we originally have 32-bit values. The lower part of those are separated. The result is calculated in R4. The upper part is separated, and the result is calculated in R5. Now the results are ready. As far as the lower part, it is in R4. As far as the upper part, it is in R5. Now we add those together and generate the final result in R3. You might wonder why this XNOOP instruction is sitting here. The reason is the multiply instructions typically take 2 cycles, and so we want to allow enough latency before the results are ready. And this one assumes that there is no hazard checking done by the processor, so we have to implement the hazard by giving enough latency through a NOOP, and once the result is available here, then it has to be added so that we can generate R3. You can see that the carry and other flags are implicitly set by these instructions, are kept internally by these MPYLU and MPYHS, and then finally when we do the additions, those flags would be used to calculate the final result in R3. This example illustrates that by making use of simple instructions which work on 16-bit data paths, we are able to improve the efficiency quite dramatically. The latency for multiplying two 32-bit values would be very high otherwise. Apart from integers, what else do we need to support? Well, one of the most important data types is fixed point. What is a fixed point? Fixed point is the number of decimal points is fixed. An example of fixed point operation is 10.21 means there are 2 places of decimal after the decimal point that are implemented, and we are not going to worry about all the digits that come after that. In most of the DSP type of processing, the fixed point is sufficient enough as an approximation of floating point, and we don't really need to support the full IEEE floating point standard. Even among the fixed point, we could vary in terms of the number of places after the decimal from short to long. In most embedded systems, it is sufficient to support the short fixed point as against the long fixed points. For example, in VEX instruction set, we have different kinds of fixed point operations supported, typically at the 16-bit level as short fixed points. The instructions such as MPYLL, MPYLH, and MPYHL support these type of operations. The higher precision fixed point multiplication is typically not supported because it is very expensive, and the data types which involve higher order fixed point are quite rare. The short fixed point multiplication is best illustrated by this example over here, in which we are trying to multiply 2 operands A and B, and what we have is a low precision 16-bit representation of A and B, which is sitting in registers R1 and R2. Using that representation, we have a instruction MPYLL which multiplies those fixed point values, 16-bit fixed point values, and generates the result in R3. We are putting a XNOOP here again to allow enough latency for multiply to complete. But once we have the result available, we right shift it to get that most significant bit in place as a result. So what happens during this process here is we start with the 16-bit representations in R1 and R2. We generate the result, might generate the result, and most significant bits might in fact reside in the carry and so on. And that is why we carry out right shift here to bring that carry into the correct position so that we have the right result available. This is illustrated over here. If we have 0.5 multiplied by 0.5, it might generate 0.25 as the result, and then we carry out a right shift which is approximating that result to the desired value over here. So in other words, most of the times we are not interested in the complete highest precision that is available from 16-bit results, because remember, if we multiply two 16-bit results, the highest precision could be available only when we support 32-bit operands. So the approximation here is we start with 16-bit and we also end up at 16-bit by carrying out these few operations here. If multiplication is expensive, division is even more expensive. So what happens to integer division? How do we support it? As you can imagine, when we divide an integer by the other, the result may be an integer or it could be a floating point number. And so in order to completely support the integer division, we'll need a floating point unit. Now in embedded world, if there is no support for FPU, full integer division is rarely supported. For example, in VEX, div-s instruction is provided for basic component of an integer division. This could result in loss of precision. A 32-bit non-restoring division could be very expensive and could take as high as 35 cycles. Many times, the compilers optimize shorter divisions by choosing simpler instructions such as div-s. Sometimes compilers even perform the division at compile time. How? If the constant is involved, they will perform the reciprocation of that constant and convert the division into a multiplication. Divisions are rare and their performance is not that critical. So what is more important here is the code size. And so approximation is introduced rather than implementing the division through an elaborate set of instructions and then reconciling those results. Having discussed the integers as well as fixed point data types, let us now test our knowledge of the operations that are performed on the fixed point data types such as multiplication. So here are different questions. Check all the statements that are true for fixed point multiplications. First statement is, can produce results that have more bits than the operands. Is this statement true or false? The second statement is, the results must be rounded or truncated to fit within the same number of bits as the operands. Third statement is, there is no loss of precision in the fixed point multiplication. Fourth statement is, all computer languages include built-in support for fixed-in values. And the last statement is, almost all relational databases support fixed-point arithmetic. As you can see here, the last two statements are, how prevalent or general is fixed-point computation? Please go ahead and write your answers now. Let's check the answers. So the first statement, whether fixed-point multiplication can produce results that have more bits than the operands, that statement is true. Obviously, as we have been talking, two 16-bit operands can produce a result as large as 32-bit. The second statement, the results must be rounded or truncated to fit within the same number of bits. That is of course true, which implies from the first statement. If the original result is large, which is 32 bits, it must be rounded or truncated to fit it within the 16 bits. The next statement, there is no precision loss in fixed point multiplication. Now, of course, this statement is false. The next statement, all computer languages include built-in support for fixed point values. This statement is also false because fixed point is a special data type that is involved mostly in the DSP side. What about the last statement? Do all relational databases support fixed point arithmetic? The answer to that is again yes, because many of these databases do support a lot of data types that need fixed point arithmetic support. Finally, before we leave the fixed point part, let us see how a fixed point number typically gets represented. So we typically have a sign bit, then we have an integral part. There's an implicit binary point here, and this one supports the precision of 4 binary bits over here. So there is a fractional part which is supposed to be for the fixed point operand. You can see here that in this representation we cannot support infinite precision, and so therefore the precision that we support is limited. Another important aspect of embedded processors especially is about saturated arithmetic. What is really saturated arithmetic? Saturated arithmetic is when you try to exceed the precision that is allowed for that implementation. This condition arises frequently in embedded processors because, as we have seen, many embedded processors support fixed point arithmetic. Before we get into embedded processor, let's see how the C supports the semantics of saturation. What C semantics supports is what is called as a wraparound. In other words, all those bits which overflow or underflow try to go back to the same operands starting at the other end of the operand. So you can see what happens here. We have a fully occupied 32-bit integer with all bits being 1, and if we add 1 to it, the result happens to be 0. Obviously, this is an overflow here, and the value itself is equal to 0. Now, as far as the regular processing is concerned, this is absolutely fine because that carry will be used in carrying out the addition further down the road or will be used as a part of the representation. However, in many embedded domains which involve fixed point operations such as audio and video, having the result which is truncated, which looks like just the 0, is not acceptable. So what is done in such cases is to support what is called as a saturated arithmetic, which is specialized for the fixed point representation. Compute the following values. Assume the valid range for numbers to be -100 to +100. In those boxes, please go ahead and fill your answers under the saturated arithmetic. 40 plus 50, 40 plus 60, 40 plus 70, 5 times -25. The next one is 40 times 40, and the last one is 30 times 5 minus 30 times 1. Please go ahead and write your answers in these boxes assuming saturated arithmetic. The first answer is 40 plus 50 is equal to 90. It falls below the maximum value 100, so the answer stays the way it is, equal to 90. The second one is 40 plus 60 is equal to 100. It is equal to the maximum value, so it stays where it is, and the answer is 100. The next one is 40 plus 70. Here the value actually should be is equal to 110. However, the maximum number in our number system is 100, so the right answer here is 100, and the value of 110 will get clipped to 100. 5 times -25. The answer is -125, and the min value is -100. So the answer is -100 because that is the lowest value we have in our system. 40 into 40. The answer is 1600, but the maximum value is 100, and therefore we must limit the maximum value to 100, and the answer is 100. Finally, 30 times 5 minus 30 times 1. 30 times 5 is equal to 150, and 30 times 1 is 30, and we are going to subtract the first answer, which is going to get clipped from 150 to 100, and then we are going to subtract 30 out of it, and so the final answer is 70, and that's what we got here. So this is an interesting one because remember, first we carry out the multiplication, and since it exceeds 100, we have to clip it to 100, and then we subtract the value 30 from it, and that gives us an answer of 70. Let us see how these instructions now operate to implement the addition and how to keep the maximum value below the allowed limit. So we have here an add operation. Add R3 is equal to R1 plus R2, and that is implementing an addition here, and the result is in R3. The question is, how do we limit the value of R3? And what the hardware does here is, first it takes the maximum of the value that is in R3 and this particular value over here, and that tells us what is the least possible value we can have in R3. For example, we could have R3 is equal to -125, but if the other value is giving us -100, then the maximum of these two values is -100, and R3 will be limited to -100. Secondly, we need to clip the RC's value at a particular maximum value. How do we do that? So again, consider the addition. What we do in this particular case is we take a min of the actual value of R3 and this particular number. In other words, this clips the value to this particular number. So let us again consider an example that the RC's value is 125, whereas our maximum value in saturated arithmetic is 100, and taking the min of the two gives us this particular number, 100, and that's where we clip this value. So in last few slides, we saw what are the differences between arithmetic saturation and how can we implement them in embedded setting. Now let's look at the next concept, which is the SIMD computing that is undertaken by VLIW. So remember, VLIW is very different than SIMD processing. Let's understand the differences between VLIW and SIMD. So in SIMD instruction sets, as you know, there are multiple data items on which we are going to work on, and a same instruction works on multiple pieces of data, whereas in VLIW, in a concurrent setting inside one long instruction, we could have different instructions. So one could be doing an addition, second could be doing a subtraction, third might be multiplication, and so on. So this shows a VLIW sort of an architecture here. This function unit might be an adder, this might be a multiplier, this might be a division, this might be doing a load, and so on. As against the VLIW, in SIMD setting, however, we have the same instruction which is working on different operands. So in other words, we may have 4 different multipliers here, but they are all still doing the multiplication. They have different data associated with them, and that's why each of these function units is attached to its own register file. So the separation here is in terms of the different data items. This data item has to be held in a different register file than that one, because that would create a very high bandwidth in terms of processing the data items. Again, all these different units could be the same, such as multipliers, or all of them could be adders, and so on. Now we do have something interesting, which is also called as micro SIMD parallel subword architecture. Let us see how that works. So here is an example of a 64-bit function unit that can process words as 164-bit or 232-bit or 416-bit or 8-bit. What that means is the long word that we have, which is 64-bit wide, can be partitioned into different pieces. It could be a combination of individual bits, 1 bit at a time, so 64 of those could be processed, or it could be 16-bit words, 4 of those, which are packaged as 64-bit here. So you can see that we operate here on subwords, that is within a word. We group those bits into subwords and we operate those as one unit. Now if you do that, for example, for 4 16-bit subwords, we have a SIMD kind of a processing going on there, but that SIMD processing is on a subword as against doing it on the full register. What is the advantage of this? The advantage of this is, for many multimedia types of processing, a lot of data can be compacted and can be fit into a long word such as 64-bit. However, each of those data items can still be 16 bits, and we can operate on 4 such data items at the same time, fitting them into this large register and fitting them into one large word. Now, this type of parallelism can speed up processing, as you can see here, and also reduce the data segment requirement, because now you have fitted all that data without wasting any bits into 64-bit long word, as against taking 4 64-bit long words if we had not put those together. Let us clearly understand these differences now for different types of processors: MIMD processors, SIMD, superscalars, VLIW, and micro SIMD. And let's see what kind of instructions are needed for supporting a parallelism of degree 4. As you can see here, MIMD processor consists of 4 different cores. Each one of them will execute different instructions, so we need 4 different instructions here. SIMD processor, on the other hand, would need only one instruction, but it would operate on 4 data items, so it will need 4 different data items, but it will just need one instruction here. A superscalar will again need 4 different instructions, each operating on different pieces of data. On VLIW, we'll have a long instruction here, which will consist of supporting 4 different operations. Remember that there is only one instruction, however, which is called as a long instruction, and that long instruction supports different operations because they are embedded in it. Finally, for micro SIMD, again we'll have just one instruction, just like SIMD. However, this will operate on one long word here, and within that long word, as we saw in the last slide, we'll have subwords, maybe 4 16-bit operands and so on, which we'll operate on. So we have been talking a lot about VLIW, and we talked to some extent about SIMD as well, but micro SIMD deserves a special attention. Micro SIMD is extremely popular, has in fact made its way as extensions for x86 such as MMX, SSE, SSE2 and 3D Now. They were all multimedia extensions for x86 to carry out the processing using the existing instructions without introducing new instructions, but asking them to manage the subword level data. So what we have here is just a different implementation of, for example, what an add means. Instead of adding just regular 32-bit operand, this add is now going to support 2 16-bit operands, for example, therefore implementing the micro SIMD parallelism. In embedded world, the manipulation of subwords is even more important, and not only the subwords are there, but they are also configurable many times. So for example, one could take a 64-bit long word and configure it as 2 32-bit words, or 4 16-bit words, or 8 8-bit words. This is to support different types of application requirements which vary in terms of precision and representation. For example, 8 bits would be sufficient to represent all possible values in, for example, audio, but they may not be enough for supporting the video, in which case we have to go to 16 bits. For high resolution images, maybe we'll have to do 32 bits and so on. What microSIMD facilitates is what is called as a lower level optimization, so that we are able to do a data compaction and we are also able to speed up processing. Let us now see how we can write a simple microSIMD program. What we have here is an original program in which we are trying to add two arrays A and B and hold the result into C. Now if you want to use the microSIMD parallelism, let's say by breaking down the 64-bit word into two 32-bit words, this is how we could do it. We maintain the original pointers to those arrays, and then we use a instruction which is a special instruction for microSIMD, which is called as P1L4. What it does is, it goes to those original words, picks those up, breaks them down into subwords, and adds 4 of them together. Instead of adding 2 of them in the original program, we are going to do 4 of them addition over here. Why 4? You can see that we were adding only 2 operands here. Now part of the array A and part of the array B, which is 32-bit, is going to get added, and the other part of array A and the other part of B is also going to get added. So that's why we have 4 operands over here, and then we will generate the result still in CP. So you can see that we have speeded up processing here by doing some parallel operations here as against over here. However, in practice, implementing microSIMD is quite interesting, and also one has to be careful about this. What are the first set of issues that are faced? Alignment issues. That means, remember, the data has to be on the right word boundaries, and that's always assured by an architecture. But now, if you're breaking the data into subwords, one must make sure that the data is aligned on subword boundaries. So one of the difficulties is that many times the structure that contains the subword elements rarely align cleanly to the word boundaries. In rare events, the decomposition of word into a subword is as clean as taking a 64-bit word and cutting it into two 32-bit words. If that is not the case, then we need to cut it in a different way, and not only we need to cut it, we need to align it. Many times, to align the data, we have to take a loop and generate some code which doesn't execute inside the loop, and what we call is as pre and post loop code. And then many times we face yet another set of challenges for holding the intermediate values of the subword results. So the subwords may not be as clean as, hey, take the first higher order bits, add them, and hey, then take the lower order bits and add them, and they can be just juxtaposed or put side by side. It may not be as simple as that. We might have to generate a result for a subword, result for another subword, and then do some post-processing to put them together rather than just putting them side by side as a part of the result. Some other complication of microSIMD processing is that they must respect the original control flow. In other words, the microSIMD code should mimic the existing branches, and what that means is sometimes the results that are generated must be predicated in terms of suppressing them, providing masks on them, and so on. Here is a real example that shows what we talked about in the last slide in terms of predication. What we have is an if condition. If AI is greater than X, then do these different operations. So as you can see, as per the original loop semantics here, whenever AI happens to be greater than X, we are going to do AI plus BI. If that condition is false, however, we are going to do AI minus BI. So now let us see how this loop can be implemented using microSIMD operations. We have an interesting representation of this loop in terms of what we call as doing a select operation first. So we can easily see here that we can take all these AIs, compare them with XS on a microSIMD boundary, and generate all those results into P condition. Then what we can do is we can take the subwords, taking part of A, part of B, and adding them, and again on those subword boundaries generate the addition side of the result. Similarly, using the subword level parallelism, we can take again part of A, part of B, do the subtraction, generate the results, and keep them ready in T sub. Note that these are different words which are on integer boundaries, and all they are doing is keeping the sub results of these different operations that we have parallelized on subword boundaries. Finally, you can see that as per the original program semantics, we should either assign this value to CI or that, but not both. So how does that work? Well, we have a nice instruction here which is called as pSelect. What it is going to do is go to that P condition, look at each one of the bits which are stored here as a result of the comparison that took place over here. Depending on the setting of the bit, if it is true, it is going to commit the tadd to CPI. If it is false, however, it is going to take that result which is in T sub and store it in CPI. So you can see here that the parallelization is not as simple as breaking the data down, adding it, and just putting it in the destination. In order to implement the condition, what we have done is first we have tried to parallelize the condition itself, and doing that on subword boundaries helps us. Then the next thing that we do is we are going to parallelize that operation of addition, again going into the subword boundaries, similarly for subtraction, and then finally over here we are going to take either this or either that and then put it over here as per the condition that is set here. Some other complication of micro-SIMD processing is that they must respect the original control flow. In other words, the micro-SIMD code should mimic the existing branches, and what that means is sometimes the results that are generated must be predicated in terms of suppressing them, providing masks on them, and so on. Here is a real example that shows what we talked about in the last slide in terms of predication. What we have is an if condition. If AI is greater than X, then do these different operations. So as you can see, as per the original loop semantics here, whenever AI happens to be greater than X, we are going to do AI plus BI. If that condition is false, however, we are going to do AI minus BI. So now let us see how this loop can be implemented using micro-SIMD operations. We have an interesting representation of this loop in terms of what we call as doing a select operation first. So we can easily see here that we can take all these AIs, compare them with XS on a micro-SIMD boundary and generate all those results into P condition. Then what we can do is we can take the subwords, taking part of A, part of B and adding them, and again on those subword boundaries generate the addition side of the result. Similarly, using the subword level parallelism, we can take again part of A, part of B, do the subtraction, generate the results and keep them ready in T sub. Note that these are different words which are on integer boundaries, and all they are doing is keeping the sub results of these different operations that we have parallelized on subword boundaries. Finally, you can see that as per the original program semantics, we should either assign this value to CI or that, but not both. So how does that work? Well, we have a nice instruction here which is called as pSelect. What it is going to do is go to that P condition, look at each one of the bits which are stored here as a result of the comparison that took place over here. Depending on the setting of the bit, if it is true, it is going to commit the TAdd to CPI. If it is false, however, it is going to take that result which is in T sub and store it in CPI. So you can see here that the parallelization is not as simple as breaking the data down, adding it, and just putting it in the destination. In order to implement the condition, what we have done is first we have tried to parallelize the condition itself, and doing that on subword boundaries helps us. Then the next thing that we do is we are going to parallelize that operation of addition, again going into the subword boundaries, similarly for subtraction, and then finally over here we are going to take either this or either that and then put it over here as per the condition that is set here. Some other complication of micro-SIMD processing is that they must respect the original control flow. In other words, the micro-SIMD code should mimic the existing branches, and what that means is sometimes the results that are generated must be predicated in terms of suppressing them, providing masks on them, and so on. Here is a real example that shows what we talked about in the last slide in terms of predication. What we have is an if condition. If AI is greater than X, then do these different operations. So as you can see, as per the original loop semantics here, whenever AI happens to be greater than X, we are going to do AI plus BI. If that condition is false, however, we are going to do AI minus BI. So now let us see how this loop can be implemented using micro-SIMD operations. We have an interesting representation of this loop in terms of what we call as doing a select operation first. So we can easily see here that we can take all these AIs, compare them with XS on a micro-SIMD boundary and generate all those results into P condition. Then what we can do is we can take the subwords, taking part of A, part of B and adding them, and again on those subword boundaries generate the addition side of the result. Similarly, using the subword level parallelism, we can take again part of A, part of B, do the subtraction, generate the results and keep them ready in T sub. Note that these are different words which are on integer boundaries, and all they are doing is keeping the sub results of these different operations that we have parallelized on subword boundaries. Finally, you can see that as per the original program semantics, we should either assign this value to Ci or that, but not both. So how does that work? Well, we have a nice instruction here which is called as pSelect. What it is going to do is go to that p condition, look at each one of the bits which are stored here as a result of the comparison that took place over here. Depending on the setting of the bit, if it is true, it is going to commit the tadd to CPI. If it is false, however, it is going to take that result which is in tsub and store it in CPI. So you can see here that the parallelization is not as simple as breaking the data down, adding it, and just putting it in the destination. In order to implement the condition, what we have done is first we have tried to parallelize the condition itself, and doing that on subword boundaries helps us. Then the next thing that we do is we are going to parallelize that operation of addition, again going into the subword boundaries, similarly for subtraction, and then finally over here we are going to take either this or either that and then put it over here as per the condition that is set here. Here is the next example which shows how nicely we can use this parallelism in a way to generate the sum. So let's take a look at the original program here, which is generating the sum through repeated additions or accumulations into the variable sum. This is a sequential program and it produces the results after it iterates for n iterations. However, now let us see how we can parallelize this program using microsymd. What we got here is a temporary variable called psum. What is it doing? Psum is doing the partial sums of the microsymd operations coming from the original array. So in other words, the original array has been decomposed into microsymd subparts or subwords, and we have this P1L4 which is taking that decomposed array, adding parts of it together, adding it to psum and storing it in this psum again. So the parallel operations of sum are speeding up things here. And these partial sums that are being produced over here are different partial sums in psum. Finally, what we have here is preduce, which is going to take all those partial sums and then generate those into the sum. Now you might wonder how is this implemented at the architecture level. What we are showing here is a simple imitation of what is going on at the program level. However, as you must note, each one of these psums here is evaluated in a separate register. And finally, we have a separate instruction which takes those registers and combines the results and produces the result over here. Why is it so? It is so because the decomposed microsymd operations produce a result and produce them for each instruction that executes separately, such as padd, and those results are held in the registers. Now it so turns out that finally after all those results are generated, we do have a preduce instruction which takes those and generates this sum. So to be clear, for this type of implementation to work in architecture, we would need a support that each one of the padd results in its own values which are separately kept for individual instructions in its own register. And then finally all those registers have to be made available and added together to produce this sum. How would this work? In a real architecture, we would have what is called as renaming mechanism, which will generate new register names over here, and finally it will consume those here. So let us summarize the importance and pros and cons of microsymd operations. Microsymd operations can achieve impressive results with minimal hardware complexity. However, microsymd is rarely implemented for the whole instruction repertoire. It is specifically done for some operations which are beneficiaries of microsymd parallelism, such as for addition. Rarely it would be done for division, for example. It is rarely done in an automatic way by the compiler. Why? Because it is a difficult job of a compiler to really reason about the microsymd parallelism without hints. What could be a complication here? The complication here could be the operand widths, which are unknown to the compiler. And in all practical purposes, one does need to do some manual code restructuring by peeling some loops, by aligning the variables and so on. And that's why microsymd parallelism exploitation is many times a bit of a manual effort. Let us now check our knowledge about microsymd and how it compares with the other processors such as VLIW. So here is a quiz. Please check all the statements that are true here. The first statement is VLIW is more efficient than microsymd for media processors. The second statement is, for the same number of addressable registers, micro-SIMD architecture holds more multimedia data than superscalar or VLIW architectures do. And then the third statement is, micro-SIMD architecture supports data parallelism but at a much higher complexity of register ports. Please put your answers now, putting a check mark against the statement that are true. VLIW is more efficient than micro-SIMD for a media processor. Is that true or false? It is false. Since micro-SIMD can pack a lot more data, it allows not only a higher amount of parallelism, but it also allows much compact data segment. What about the second statement now? For the same number of addressable registers, micro-SIMD architecture holds more multimedia data than superscalar or VLIW architectures. This statement is true. That is because micro-SIMD allows you to deal with the sub-word level parallelism. In other words, for a large word such as 64-bit wide word, micro-SIMD allows you to pack, in fact, 8-bit words. What about the last statement now? Micro-SIMD architecture supports data parallelism, but at a much higher complexity of register ports. This statement is also false. The complexity of register ports is higher in VLIW. Now here is a quick comparison in terms of storage capacity and area requirements for fixed number of bits per register across different kinds of architectures: MIMD, SIMD, superscalars, VLIW, and micro-SIMD. What we have here is a fixed number of registers, which is 32 per register file for all of them for a fair comparison. We also have the width of the register as 16-bit, again for a fair comparison. And in case of micro-SIMD, because we are going to have those 4 subword operands, we have the width as 64-bit. Now, with these restrictions, in order to support a parallelism of 4, we are going to need number of registers file as 4 in MIMD, also 4 in SIMD, and the rest of them is going to have 1 register file. The total number of registers is going to be 128 for both MIMD and SIMD because of the 4 register files, whereas they are going to be 32 for other configurations. As you can see here, the maximum number of operands that can be handled under these different configurations are as follows. For MIMD, it is 128 operands. For SIMD, it's also 128 operands. For superscalar, there are going to be 32 operands. For VLIW, there are going to be 32 operands. And as you can see here, for micro-SIMD, we again are going to have 128 operands. So I'd like to draw your attention to a few things here. The number of operands here that is supported under micro-SIMD is 128, and so it is 128 under both SIMD and MIMD. So you can see that micro-SIMD is able to support a very large number of operands just like SIMD and MIMD does. However, micro-SIMD does it using just 1 register file, whereas SIMD and MIMD do that using 4 registers file each. You can see that therefore the same number of operands is supported using a fewer number of registers files in micro-SIMD. Now, what is the catch here? There is a cost, of course, associated with micro-SIMD. The width of the register here for MIMD and SIMD is 16-bit, whereas the register for micro-SIMD is rather wide, which is 64-bit. So the question is, if you have a regular size register such as 32 or 64-bit, you can still go ahead and support the micro-SIMD parallelism provided you have function units which can operate at 8-bit or 4-bit or 16-bit boundaries. In terms of the other organization, micro-SIMD is clearly more powerful than MIMD or SIMD organizations, and in fact even more powerful than VLIW for that reason. Now, the comparison with respect to VLIW should be weighed not only in terms of the registers, but what kind of operations we can do. Remember that micro-SIMD can do only specific operations, whereas VLIW is geared for much more general purpose parallelism. In other words, in micro-SIMD, you still have just one instruction which is doing adds across the board, whereas in VLIW, in those 4 slots, you could execute 4 different kinds of instructions. So in other words, VLIW supports much more general parallelism than micro-SIMD. So far, we have been discussing many different aspects of the processors in terms of the microarchitectures. One of the most important aspects that is we are going to finally discuss is all about constants. That is the support for immediate operands and literals, and these are the constants which become a part of instruction, and they are a part of the operand field in multiple different ways. Many of these constants are already known at compile time, and some of them are known at load time. In other words, after linking the program and just right before it is loaded for execution, some data is made a part of this, and those are the load time constants. Typically, a short constant, an unsigned constant, which is a part of the immediate addressing mode or which is a part of the immediate operand, fits in the single encoded operation. Many times, even a long immediate operand is a part of encoded instruction provided it fits the data path width. There are two popular mechanisms for handling long immediate operands. Sometimes that immediate operand is broken down into two parts, and you use two instructions for loading those parts separately, such as load low and load high. And then sometimes either those operands are too long or it is not possible to break them down, so we use what is called as memory allocated mode. How does the memory allocated mode work? Well, the compiler allocates the long immediate operand in memory and then loads those operands through an instruction. So the operand is not really a part of an instruction, but it is loaded as though it is some data value which resides in the memory. So what are the other kinds of constants that could come as a part of instructions? Many of them could be values, as we saw, which are used through immediate addressing mode, but that's not all. What about branches? Many branches are also relative, and branch offsets are an important part of constant operands, which are a part of instruction. So the operand field as part of instructions that deals with branches has to do with the size of the branch offset. Typically, the branch offset is designed to make the jump happen across the largest possible area where the branch is supposed to go. For example, in MIPS, the jump instruction has 26 bits wide offsets that allows you to span an address 2 to the power 26 as a value. In fact, PC is word aligned in MIPS, which means that you can jump to a word aligned location, in fact, and you can jump 28 bits. Also, MIPS has PC relative addressing and many other modes. What about embedded processors? Most embedded processors are 32-bit ISAs, and they include a branch offset large enough to cover local branches. In other words, we rarely have very large branch offsets in embedded because the programs tend to be short and the jumps need to be local. In architectures such as ARM, there are in fact shorter branch offsets. So what if you have a very large branch to cover and you don't have a large offset? In such cases, the solution that is adopted is by chaining the branches. The compiler creates a branch which trampolines to another location, from there uses another branch to carry out the jump. Through a chain of such branches, you can reach your destination PC address. What about 64-bit address spaces? How are they covered? Again, the principle that is used to cover 64-bit address spaces is exactly the same. You again use the trampoline. From your source, you carry out one jump that takes you to another PC address, where there is another jump which takes you to a third one, and this chain eventually reaches your destination address. And for that reason, you do not have to have very large branch offsets as a part of your ISA. We studied data paths and ISA considerations in this lesson. So you should be able to answer the question I posed in the introduction. What do we need in an embedded system to complete a peculiar task? It is a bit of a trick question. The answer is, it depends on the task. Embedded systems are geared towards different tasks to behave in different ways, and therefore they are highly tuned to the tasks that they perform and are different for different tasks.